Good morning and afternoon. Thanks for joining us, everybody. My name is Janie Montblanc, and I'm the coordinator for the Great Basin Science Delivery Project. Welcome to our webinar, Assessing the Relationship Between Ground Measurements and Aerial Image Analysis of Land Cover Classes in Pinyon and Juniper Woodlands, presented by April Hulet from Brigham Young University. Before I introduce our speaker, I want to let you know that you may ask questions at any time during this webinar by typing them into the questions pane of your control panel at the top right of your screen. In past webinars, we waited to field questions until after the presentation, but we're going to try something new this time and take questions throughout the presentation. So if you have a question, type it into your questions pane and I will field it to April during the presentation. We're also going to try another new feature for this webinar, and that is the webinar polling feature. The Great Basin Science Delivery Project is developing ways that we can assess whether or not we're doing a good job of our information exchange mission. So we wrote 3 questions about the webinar today and we'll submit them toward the end of the webinar. If you can help us out by responding on the no to yes scale, we'd really appreciate it. Thanks. Now I would like to introduce our presenter. April Hulet is a doctoral candidate working with Dr. Bruce Roundy studying wildfire fuel reduction treatments. Her work employs color, infrared, multispectral, and other remote sensing and geographic information system technologies to 1. Assess the relationship between ground measurements and remotely sensed measurements, and 2. Develop techniques that can be used to reduce field data collection, for monitoring and assessing pinyon and juniper woodlands. Welcome, April, and thank you for being here today.
Thanks for the introduction.
Oh, right. I have to make you the presenter, don't I? Sorry about that.
Yep, no, you're okay.
Okay, there you go.
Okay, so you can see my screen now?
Yep.
Okay, well, thanks for that introduction. As was stated, this presentation is going to be looking at assessing the relationship between ground measurements and aerial image analysis of land cover classes in pinyon and juniper woodlands. And before I get too far in, of course this wasn't done alone. I just want to hurry and thank my collaborators, Bruce Roundy, Steve Peterson, Steve Bunting, and Ryan Jensen, as well as acknowledge our funding sources. We're part of the SageStep project, and we were funded through the Joint Fire Sciences program, as well as BYU and the University of Idaho. And also thank the BLM and the Forest Service who implemented a lot of the treatments that we'll be looking at today. So most everyone here probably is familiar with the idea that pinyon and juniper woodlands have experienced a significant tree infilling and a major expansion in their area over the last few hundred years. And they're going into areas that were once dominated by shrubs and other herbaceous vegetation. And as we see this infilling of our trees and the expansion, there's several different results. One, we see this loss of understory vegetation and composition, which is declining the ecological functions of these systems. With the loss of understory cover, we are also seeing an increased potential for soil erosion and runoff, as well as soil hydrophobicity. We're also seeing an increase in the potential for intensive crown fires as these canopies begin to touch. So our objective today is to really provide land managers with tools that can help them assess vegetation composition and bare ground that they can then use to evaluate and manage and restore their, or understand what they can do to better restore these SageStep communities that are encroached by pinyon and juniper trees. Our primary objective then is to test the accuracy of object-based image analysis cover measurements from high spatial resolution imagery relative to ground measurements on pinyon, juniper woodlands where fuel reduction treatments have occurred. And that's kind of a lot to think about initially. So throughout this presentation, we'll break this down into more usable units. First, we'll talk about pinyon and juniper woodlands where we're doing this work, and also the fuel reduction treatments that we'll be looking at today. We'll discuss, second, our imagery, what was collected, as well as the object-based image analysis, which is the technique we've chosen to classify these areas for our study. And then finally, we'll talk about the results. And ideally, we want to show some examples from our research that could potentially be used to quickly and accurately assess the understory and overstory cover in these expanding woodlands. One, we can provide valuable data for planning and designing future fuel reduction treatments. Two, we can evaluate the longevity of these treatments and ideally prioritize where maintenance treatments should occur. And three, it will also increase our understanding of the spatial distribution and cover of these fuels following treatment. So our study is part of the Sage Steppe project, which is a regional study evaluating methods of sagebrush steppe restoration in the Great Basin. And our study focuses on 5 pinyon juniper woodlands. We have 2 that are western juniper sites. We have 1 in Divine Ridge and a site at Blue Mountain, which is in Northern California. We then go over to eastern Nevada, where we have a marking corral site, and we have both pinyon and juniper found at this site. And then we have 2 different sites in Utah that are dominated by Utah juniper. So this kind of gives us a range of pinyon juniper woodlands across the Great Basin. Our sites cover all woodland phases of encroachment, meaning that they range really from phase 3 all the way to phase 1. As you can see in the pictures, our phase 3, which is the picture on your left, is an area where trees are more dominant and they're heavily influencing the ecological processes of the site, versus our phase 1 where we have more of a shrub and perennial grass component, which are influencing the ecological processes. Our fuel reduction treatments that occurred on these sites across this gradient of tree dominance include a prescribed fire, which occurred in the fall at all of our sites. Most of our sites were treated in 2006, with a few in 2007. Individual subplots, which is the scale we'll be looking at, were hand-burned later, which we will see in a minute. We also have a cut and drop treatment where they cut all trees that were taller than 0.5 meters or half meters in height and then drop them perpendicular to the slope where possible. We also had a bullhog or mastication treatment, which consisted of shredding the trees, and this was a treatment that was unique to our Utah sites. So to briefly talk about our imagery, today we're going to primarily discuss our color infrared imagery, which was collected using the Vexel Ultracam digital camera in late June and early July of 2009. We chose to have this imagery collected during that time frame in order to capture phenological differences between our perennial grasses and our annual grasses. Generally in the Great Basin, in late June, early July, our perennial grasses reach or approach their maximum yearly growth, and often our annual grasses, such as cheatgrass, have begun to senesce. So ideally, this provides a spectral difference between our perennial and annual plants that we could pick up aerially. Once our imagery was collected, we extracted individual subplots from the larger treatment area. And this is what you're looking at in this imagery. We have 4 different subplots, which are 30 by 33 meters. In order to extract them, we collected 2 GPS points, one in the center of each plot and one in a designated corner, that we then used to georeference onto from our larger imagery. Here we are looking at our treatment subplots. So I just wanted to give you an idea of the range of values that we're seeing. And maybe I'll hurry and scroll back one. And this one we're looking at untreated woodlands, and these are all 30 by 30 meter plots across our site. So you can see that we are capturing quite a variation in our imagery. The top 2 are Blue Mountain and Divine Ridge. Those are our western juniper sites. And then you can go down and look at the marking corral site, which is in the lower left-hand corner. And at this site is where we have both single-leaf pinyon and Utah juniper. So we will show you techniques on how we distinguish those 2 species. And then at the Aniki site, I wanted to show you a phase 1 subplot that we evaluated where we have a substantial shrub component. So as we go through our results, you can keep this in mind, these variations within our sites. Okay, so here again is our treatments. You can see our prescribed burn. I just showed two different site locations. And obviously the prescribed burn is going to be dependent on weather conditions, the day of the burn, as well as the heterogeneity of the landscape. So you can see at Anarchy, we most likely had a less severe burn. We still had quite a few branches and needles retained on our trees. Also, you can see that these little green patches or circles are actual perennial grasses in this image. And over here, this is our Divine Ridge. You can see where we had our black soils following our burn. And again, these burns took place in 2006, and so this is about 2.5 years later that we collected this imagery. Here is a visual of our cut and drop treatment. You can see the two different locations. We have Stansbury and Blue Mountain. Again, our western juniper areas, which are Blue Mountain and Vine Ridge, you can see that we have different soil types than we do over in Anarchy and Stansbury, which are going to be a factor in our classification. Again, both of these treatments are about 1.5 years old when our imagery was taken, and the interesting thing is you can still see all the needles that are retained on the image, or on the trees that have been cut. And then this is our bull hog example. And in our bull hog, this was specifically at our Utah sites. And the bull hog is actually this gray material that you can see up here in the top left corner. And it's the actual shredded trees. With our bull hog and our cut and our prescribed burn, essentially we're moving a lot of the overstory canopy. And so as we look at the results, keep that in mind as well. So we chose to do an object-based image analysis, and basically what that entails is that we aggregate pixels into meaningful objects based on certain criteria. So they look at neighboring pixels and then create the image object from there. If you look at the bottom 3 images, I just wanted to show a quick example of what we're talking about when we say object-based image analysis. The far left one right here, you can see that we have individual pixels, which is traditionally used by most classification processes. We then move over into these next 2 pictures where we are forming objects. And essentially what you're doing is you're decreasing the level of detail as you create these real-world objects. And there's been a lot of studies done on looking at the segmentation procedures of doing this type of analysis. And we also investigated quite a few different classification practices, and what we decided is you should use the segmentation process that best represents the line cover classes that you are interested in. And for our study, we actually decided to use this middle classification, which is smaller than this one on the left or on the right. And for reasons you can see within this box, the green box right here. Up in the top left-hand corner is our unsegmented image. And from that, we can see that in that box is most likely a shrub. And you can see that when we have our scale too large, we're actually incorporating this shrub species in with probably a tree object. So oftentimes we found that our classification accuracies decrease as we increased our scale. But here we found that we could still get pretty good differences between our segments and objects, and instead we could use the technique of merging different objects instead of trying to create real-life objects initially. So to do our experimental study, we first looked at training subplots. So essentially you have an area that you're interested in, and you place subplots that capture the most variation of what you want to describe. So these were not randomly selected, but instead placed to capture that variation. Typically, we had all 3 phases of woodland that we wanted to describe in our classification models. And that really is a crucial step when you're trying to apply this to any other kind of practice, is that you have to capture that variation. From these training plots, we then developed rule sets or process trees to classify our line cover classes, which in this case consisted of shadows, live trees, bare ground, shrubs, herbaceous vegetation, and litter. One of the nice things about eCognition, which is the program we chose to use for our object-based image analysis, is that you can take a hierarchical approach when you're doing this classifications. So basically, once I classified, for example, live trees, those objects are masked out from my further classification unless I specifically tell it to go back and reclassify certain objects. So we did choose to use eCognition Developer, but there are other programs out there that do the object-based image analysis, such as feature extraction, which is an extension of Envy, the Envy software, or Feature Analyst, which is an extension of ArcMap. There are pros and cons to all of these different programs. eCognition has a pretty steep learning curve, but we found our best estimates using this software. eCognition, essentially, once you have segmented your image into these objects, it essentially produces hundreds of features that can be used to classify your image. And for our classifications, we primarily used spectral classifications, which are traditionally used in any kind of classification, and they're designated by the asterisks. Certain ones that were most common I listed. This is just a simplified example of some of our process trees. Typically, we probably have between 30 and 35 steps, whereas this one probably has 15 or so. Here, you can see we use mean brightness. The NDVI, or the Normalized Difference Vegetation Index, was used quite a bit. So it was nice to have that infrared band when we collected our image. We had red, green, blue, and infrared. We also used the Soil Adjusted Vegetation Index, or SAVI. We used our hue saturation and index transformations. So basically, eCognition produces a lot of different features that you can then select to classify your objects of interest. We also used spatial features to classify our image, and spatial ones are unique to the object-based image analysis. And basically, what it entails is counting up the number of pixels within an object. So you can either limit the size that you want to classify a certain object or not. Next to spectral, we probably use contextual features most. And contextual features most often used was the relative border function, which looks at the ratio between the shared border between the objects of the classified image and the unclassified image relative to the total borders. So basically what that means is when we would initially use, for example with our live trees, we would use NDVI to select an area that we knew was a live tree. And then as we approach the perimeter of that tree, oftentimes our spectral classifications would incorrectly classify it as something else. So we could use this relative border function to actually grow our trees out into the border until they were the shape that they were found in the landscape. And we also use that to deal with shadows a lot of times. With any kind of remote sensing or aerial imagery, you often have shadows. And this relative border allowed us to grow our trees out into the shadows so we could use our knowledge of the tree shape and diameter to better classify those objects. And finally, we have textural objects or textural features. In our study, we did not use any textural features, and that's primarily because of our segmentation size that we chose, where we decided to use a smaller scale on our segmentation. This eliminated a lot of our the potential for textual analysis. You typically need to do larger segmentations if you're going to use textual features. So the numbers next to each of these different features represent thresholds, and these were adjusted on each of our training subplots so that we could optimize our remotely sensed cover estimates with our ground reference cover data. And ideally with our training plots, we got each of these different classification classes or land cover classes to be within plus or minus 5% depending on the classification. So once we established these features with the thresholds, we then applied them to a validation our validation subplots, which were a secondary subset of our training subplots. So basically we wanted to see how well these rule sets worked that we created with our training subplots to describe the surrounding area. And cover estimates from the validation plots were then compared to the cover measurements of our ground data. And our ground measurements that we used in this study was from the line point intercept method, where we collected the first contact intercept data, or the top canopy vegetation or ground cover measurements, and then to estimate our cover for that subplot. We then compared those two different results from our validation subplots and our ground measurements using a paired t-test, a one-way ANOVA linear regression accuracy assessment, which we will discuss for our land cover classes. When developing these rule sets, there are really multiple ways that we could have looked at our data. And we decided to look at it on 4 different spatial scales. So initially we looked at individual sites. So we took our training samples for that particular site, adjusted the features and thresholds to best classify our land cover classes, and then implemented that across for each individual site. So essentially we had 5 different rule sets for our 5 sites. From there, we wanted to look how much we could improve if we took each subplot and adjusted or refined that threshold of the feature to better classify our subsample. We also looked at regional differences between our rule sets. We divided our area into areas that had western juniper, which was Divine Ridge and Blue Mountain, and then we also had our Utah juniper sites, which were Stansbury, Anarchy, and Marking Corral. And then we also wanted to see if we could correctly model our whole network of sites, which includes all 5 of our sites into one model. So for our regional network model, essentially what we did is we found the features that were most used to classify each land cover class in our site models and then applied those to our region and network, where we took training samples from whatever sites were included. So collected training samples from Divine Ridge and Blue Mountain to do that model, and then training subplots from our other 3 sites for the Utah juniper model to get a subsample of all the variation again across the landscape. So we took about 10% of our subplots to train on and then to validate on about 90% of the remaining ones. So we'll start by going through some of our results. We're going to look at tree cover first. Here you can see an example of one of our 30 by 33 meter subplots. Our classified trees are obviously in the bright green there. And below, I just want to take you through one of these real quick. You can see that we have broken into our 4 spatial scales. And so we have the network, which includes all of our sites across the Great Basin. We have regions, which are western juniper versus Utah juniper. We have our sites, so we have 5 different locations, and then our subplot. So below that, you can see our average mean difference between our ground measurements and our object-based image analysis different cover estimates. So in areas where we have negative numbers, those are areas where our object-based classification was less than our ground reference data. And where we have the green arrows, that means it was significantly less using our t-test. So on our network and region site, when we tried to do our line classification for trees on that larger scale, we typically underestimated from our ground measurements about 5%. Versus our site and subplot, which were not significantly different from our ground measurements. So below that, we can look at our simple linear regression that we created. We have our ground reference cover data from our line point intercept data on the x-axis, and then our remote sense cover data on the y-axis. And you can see as we go from network to subplot, you can see that correlation coefficient slowly gets greater and greater as you go. So with our site and our subplot, we were able to explain more of the variation than we were on the regional level, and there's a regional or network level. And there's several different reasons of why this could occur. Some things that we've noticed when we broke it into individual site is that there was definitely differences in canopy structures between Utah juniper and western juniper. And oftentimes our classification techniques could accurately classify one or the other, but when combined, we saw a decrease in our western juniper sites. We also had differences in shadows. Typically, we averaged about 4 to 5% per subplot of our total area's shadow, but in some instances we got up to about 15% shadow, and in our rule sets that's really hard to account for variations that can be as low as 1% all the way to 15%. So that attributed to some of our variance that you're seeing in our simple linear regressions with our region and network models. When we tried to distinguish our two different species at the marking corral site, where we had both single-leaf pinyon and Utah juniper, we were fairly successful. The single-leaf pinyon is in the bright blue, and the Utah juniper is in the green. You can see that with the Utah juniper, we were within 1% from our ground data. With the single-leaf pinyon, we were less than our ground measurements by about 2%. But overall, we felt confident in our ability to distinguish the two classes with our imagery, which is the 6 centimeter color infrared imagery. When we look at our trees or what happened to our trees due to our different treatment techniques, we have prescribed fire first. And so in that green color, we're trying to highlight our burned tree canopy. And the 12% above is our difference between our two different measurements with our simple linear regression below. And really what we found with the prescribed burn is it varied according to how intense the fire was. So in areas where we had less severe burns, where we retained more of our branches and needles, we actually had more area to work with in our classification versus a more severe burn where we may have just had the stem to classify. With our cut and drop treatment, the cut is represented here in the blue. You can see that we actually significantly underestimated it when looking at the ground data by 2%, although we had a fairly good correlation coefficient. This could be very useful as we, it can be useful in a lot of different ways. One thing is that you can evaluate, if you were to take this again and look at the tree needles on the branches and the time since treatment and evaluate when those actually drop off it, which would change the surface fuels. Oftentimes, with our classification, we would be in areas that had other dead woody material, which was picked up in the smaller polygon objects that you can see. We couldn't really distinguish if those were there before treatment or after treatment, but we definitely felt like you could capture a lot of the downwoody debris from the cut and drop treatment. And then here's our bull hog results. Again, we were fairly accurate in our classification using our imagery. One of the values that we're seeing in this with our treatments is that we can really look at the continuity of our surface fuels and then apply those to fire behavior models. So, yep, okay. So now we're going to move to shrubs. And so it's the same setup for the rest of the time. So this is looking just at a 30 by 33 meter subplot just for a visual reference. Our shrubs are highlighted in the blue on the right image. We only saw a significant difference in the subplot, but again, at the subplot level, which was probably not what we were expecting, except you can understand why if you look down at the simple linear regressions and look at the variation. With our subplot, we had a lot tighter fit. We underestimated and overestimated shrubs less than we did with the network or regional model. With our shrub species, when we had different species that were greater than 5% of the total cover, we tried to distinguish them or differentiate them from each other. At 3 of our sites, we had both the sagebrush and antelope bitterbrush mix. We felt our overall results were quite accurate. We were 2% off on our sagebrush and also 2% off on our antelope bitterbrush. One thing we did notice, though, when we were doing our accuracy assessments or looking at our overall accuracy of how we classified, we did typically misclassify antelope bitterbrush more than we did sagebrush. And we think this is most likely an artifact of our classification technique. By merging and combining our different adjacent objects with each other, we saw that whatever species was more dominant or had a larger area typically was classified as that species.
April, I have a question.
Okay.
Scott Davis asks, did you or do you plan to compare differences according to site differences in elevation, aspect, and precipitation?
Yeah, we have compared our site differences, which will be coming out in a paper shortly. As far as elevation, precipitation, and aspect, we do have that information for our classification. We didn't use that here, but it's definitely available, and ideally we'll use that in the future to model some of our behaviors that we're seeing, some of our responses to the treatments.
Great, thanks.
Yep. Okay, so now just continue on looking at shrubs. In our cut and drop treatment, again, you can see we removed a lot of the overstory, so ideally we could capture more of those shrub species. Here in our bullhog study, you can also see our shrubs. When you're looking at the bullhog, it's interesting to notice that this area is the shrubs versus these little blacker dots, which are our perennial grass species that we'll look at in just a second. For our prescribed burn, we actually went and hand burned those subplots, and so they removed most of our shrubs. So typically they were less than 5% cover, which limits what you can actually classify. So next we have our perennial herbaceous vegetation, and this includes both perennial grasses and forbs. There were no significant differences between the two methods, but we did see some interesting trends. On average, our perennial herbaceous vegetation estimates for at our region and network level were about 10% greater than our actual ground data, and this is mainly contributed to the edge of the western juniper trees. On the Utah juniper trees, we had more compact foliage, so they were easier to classify than with our western juniper trees. Here we're looking at litter results, which includes our annual vegetation, which is cheatgrass. We weren't able to distinguish that in most cases, and unfortunately we underestimated this on all sites consistently. And this was likely due to a lot of different, or several different reasons. One, when we use the hierarchical approach to do our classification, litter was often at the bottom of our list, and we typically start with more distinguishable land cover classes such as our live trees, bare ground, and shrubs. And so litter often got put in kind of the leftover category. So our unclassified objects were classified as litter instead of actually establishing features. Not always, but typically this is how it works. Also, with our subplot extraction, where we use 2 different GPS points, we could have had small shifts in our plant communities, which definitely would have shown up more in these understory vegetation classes. Our bare ground results for our untreated plots, we're seeing the same trend. Our correlation coefficient does go up as we move from our network to our subplot. We did see some significant difference in our subplot level, but again, the decrease in variation is most likely the cause of that. To just hurry and look at some of our treatment options, here we have our prescribed burn, we have perennial vegetation cover, we have our litter, and you can see with our litter a lot of the vegetation or the litter here is attributed to cheatgrass, and then also our bare ground. Again, with our treatments, we're actually removing that overstory canopy, which is improving our classification of these smaller classes. Here we can see our cut and drop treatment. We have our perennial grasses in orange, our litter, which is represented in pink. We had probably most often our misclassification in the cut and drop was between our litter and our cut trees, the needles actually have similar reflectance values to our litter, so we had to use different techniques in order to pull that out. And then we have our bare ground, which is fairly accurate. Here's our results for our bullhog study. Our perennial grasses are in orange, our litter's in pink, and then we have our bare ground, which is in yellow. I just wanted to hurry and show an exception to the rule where we were able to distinguish our cheatgrass from our litter. And that's in an area where our cheatgrass actual cover was greater than 20%. And this is our Utah Stansbury site. And so you can see over here in our prescribed burn area that litter, or cheatgrass, is these darker patches, or these more red patches. Because we collected our imagery in June and July, we were able to see or distinguish our cheatgrass in this particular area. This is all starting to senesce versus our perennial vegetation, which is these green color, these green bunches. In the cut and drop treatment, it's a little bit more difficult, but you can see we still have patches of our cheatgrass that we were able to distinguish. And then the largest difference is in the bullhog treatment of this area, where we can see these large patches of cheatgrass. And so this should be considered when collecting your imagery. It's important to collect the right time, but also you need to have large enough patches that you can detect. At our other sites, we typically had less than 5%, and cheatgrass was dispersed throughout the plot, so meaning that there's a stalk here and there, which made it difficult to distinguish, versus something like this at our Stansbury plot, where we could classify our cheatgrass among the other feature classes. So just quickly to look at our accuracy assessments. So we wanted to see how well our classifications were. So our overall accuracy is the % of correctly classified objects. And we averaged about, well, between 80 and 85 on all of our treatment plots, which we consider to be in strong agreement with the ground data. And then we also, I just wanted to quickly show our kappa statistic, which is also another measure of accuracy, or how much better it would be, our classification is, than if you were to randomly classify an object. So if it's greater than 0.8, it usually has a strong agreement between the reference data. So we felt pretty confident about our classification for our specific land cover classes. So just in conclusion, going back to our objective statement, we wanted to look at the object-based image analysis using our 6 centimeter data and really look at comparing these to ground measurements in the different treatments. And what we found is that oftentimes our classifications were accurate enough for a lot of landscape assessment applications. For instance, at the Stansbury site, which we were just looking at with the cheatgrass, if you were to repeatedly collect imagery there, you could look at the invasion of grasses. At our other sites where we had bare ground cover, which is fairly accurate, you could use repeated photography to look at the connectivity or the changes in that bare ground, which is a function of a lot of ecological processes. We do feel like these are good techniques that could potentially complement and even reduce field data collection for monitoring and assessment, and also improve our understanding of fuel mapping, which could help us better model and understand fire behavior, as well as plan fuel reduction treatments. And also to evaluate the longevity of these treatments. How often do we have to go retreat the area, or when should we go retreat these areas? So basically, by sampling a smaller area or capturing that variation in our training samples, we can ideally collect or have data on a more operational landscape scale. So just in the last 5 minutes, I just wanted to highlight one other study that we're looking at, where we're using NAPE imagery and scaling up from our high-resolution imagery. So this is an example of our control plot at Aniki in 2006. This is zooming into a specific subplot, and then this is a comparison that you can see between that and our high-resolution imagery. So you can see the potential for NAPE imagery right there. You can see that we can most likely look at tree canopy cover, but we have a lot of mixed pixels representing the other vegetation. So basically what we found is we used the object-based image analysis to estimate our cover over a large landscape. So this is about a 400-acre plot. And you can see that in areas where we have a lot of variation, such as these areas that are probably phase 3, we have a lot of overlap in our cover. We probably misclassified some of the bare ground as actual tree cover. So what we recommend and what we did for the remaining part of our study is to break these into smaller units that capture more of the variation. So ideally we would break this into an area where we had more of our high density cover versus more of our low density cover. And by breaking that up, you can better model those variations. So we did a lot of extractions on our subplot levels. We, with the remote sensing, we did underestimate it from our ground measurement by about 2.6%. However, when we look at our linear regression, we felt like we had a pretty close relationship between the two different methods. And so to go a step further, we wanted to see, well, if we can extract this cover data, is there a relationship between other physical characteristics that would be important for things such as fire behavior models? And on the ground, we corrected the biomass of all of our trees on our subplots using the crown diameter method, where essentially you measure the height of the tree, the crown base height, and then 2 diameters. And so we wanted to look at the relationship between these biomass estimates and our cover reference measurements. And you can see that this is our ground data, our ground cover on the x-axis with our biomass estimates on the y. And we have a tight correlation. So we thought, well, if we have this correlation from our ground data, can we estimate biomass using our NAPE imagery? And so this is our initial shot at trying to correlate these two different variables, our biomass and our NAPE cover. And we got a little bit lower correlation value, and to further explain why, we broke it into more of sites and region areas. So from our Utah juniper site, you can see that with Utah juniper we have higher correlations than we did when we looked at it across the network site. And the Tausch's biomass estimates which we were using were developed on Utah juniper versus our western juniper. So we're seeing a difference between our two different species, and one can we estimate our biomass from and one can we not. And we're going to continue to do further research on this and put our measurements into fire behavior models. In addition to doing fire behavior models, we're also going to look at multiple different spatial scales. So we've used our high resolution imagery to look at NAPE imagery, but would like to expand that farther, and also evaluate different remote sensing platforms such as the hyperspectral and multispectral imagery, and really look at the usefulness of it in monitoring and assessing rangelands that can be used by land managers. So with that, I will leave it to any questions.
Thank you very much, April. So now, if there are questions, please type them into your questions pane, and I will field them to April. And I will also try this new polling feature, if I can figure out how to do it. Oh! All right. I didn't realize that took over the whole screen. Okay, I have a question for you, April. It's from Henry Bastian. Are you looking to do this type of work across the nation?
Well, that seems a little overwhelming, but yeah, I think that this type of work can occur anywhere. We are primarily focused here in the pinyon and juniper area, but we're definitely interested in finding these tools that can be used in any kind of land management applications. We all have to monitor and assess large areas, so I think it could be very useful to do across the nation.
Thank you. Next question is from Louisa Evers. What do you plan to use for fire behavior models? The original 13, the Scott and I don't know how to say it, Bergen 40, or FCCS Fuels Characteristic Class System?
Yeah, well, we're definitely considering all of those, but also some of the new ones that are coming out, the WFDSD, I think is what it's called, and also Behave Plus, which is typically used by a lot of our managers here in the Great Basin. And then Farsight is one that we are definitely considering as well.
Great, thanks. Henry Baston asks, are you looking for partners?
Yes, always. We want to extend our research and hopefully get this to apply and be used by land managers, especially as we're improving our imagery and our computer power. We can definitely start incorporating these into management decisions for planning as well as monitoring and assessment.
Great. So I guess, Henry, contact April or myself, and I will put you in contact with April.
Yeah, and up here on the question slide, I do have my email address.
Oh, right. Great.
I'm kind of in transition, so it's a Gmail account right now, but I'm definitely interested in anyone who has questions. Feel free to contact me.
Wonderful. The next question is from Dean Stacy. How would one request this type of analysis be done for a government, a government agency?
That's a good question. There's a lot of people in the academic world who could potentially do a certain assessment for a project, but also, I mean, I think these are tools that can be used by your GIS folks within the office. There is somewhat of a learning curve, but the software is fairly inexpensive, and the imagery is getting better and better, especially with our nape imagery. I mean, here in Utah, we're getting down to 1 foot imagery, which is really improving our classification abilities. So I think with a little training, you could probably do a lot of this assessment in-house, but there's also some private companies that do it.
Great, thanks. Chad Hormann asks, what would be an estimated cost for this work to be done on, say, a 5,000-acre project area?
For our study, where we collected smaller subplots, our treatment plots, we probably collected less than 200 acres at each site, and across the whole Great Basin. So it was a little bit more expensive than if you were to do one piece of land, one piece like a 5,000 acre area. Nowadays, we have this contracted out through out of a company in Salt Lake, and I know the rates are continually going down, but I think you could do it for like 3,000 or 4,000.
Okay, thanks. Next question from Louisa Evers. WFDS, WFDSS, Behave Plus, and Farsight are processors. My question involved the models that are used as inputs to the processors. Do you want me to reread the original question?
No, I remember it.
Okay.
Yeah, so, I guess I'm not 100% sure. If you have any recommendations, I'm definitely open to that.
Okay, yeah, so contact April or myself, Louisa, if you want to talk about that further. Okay, are there any further questions? I have one last poll to launch. All right, well, that looks like the last question. I just want to let you know that a recording of this webinar will be sent to you automatically through the GoToWebinar system tomorrow, and will also be posted on the Great Basin Science Delivery Project website sometime next week. Also, if you have more questions regarding this webinar, please email me or April. Oh, we have some more questions that came in. Dean Stacy asks, could we use this type of analysis in our SGI efforts?
SGI? I'm not 100% sure what that is.
I wonder if is that the Sagegrouse initiative? I believe it is.
Okay.
Yeah.
Yes. If you have high spatial resolution imagery, you can more quickly assess sagebrush cover. As far as getting down to specific forbs that might be pertinent to sage-grouse, it would be more difficult, but if you were familiar with the area, you could probably do some training subplots and pick out those areas. They're doing a lot of work using this type of imagery and modeling certain habitats for sage-grouse, and so I definitely think that there's potential for that.
Great. Thanks. And Chad Hormann asks, how does one go about getting training for this kind of work?
There's there's several different ways that you can get the training. I know when we first started, there were webinars put out by remote sensing community people mainly, but there's also quite a few different research entities within the government that are doing this type of work. And ideally with the Sage Step project, we will be developing some workshops that we can start implementing. So kind of the first step would be deciding on a certain software package that you are interested in doing, and then contacting people that are using it to set up some kind of training.
So just for my own follow-up, if someone didn't know what type of software package to use, would they talk to someone like you or someone who was doing this to ask about how the different software packages work?
Yeah, definitely. There's a lot of different people that are comparing different software packages, and even here at BYU we are. And so, yeah, feel free to contact me if you have specific questions. I can lead you to other people if I'm not sure of the answers.
Okay. Great. Thank you. Do either of you have questions? Okay. Well, thank you very much, April, for your presentation, and thank you, everyone, for your participation and for helping us out with our first polling test. So, as I said again, the recording will be sent to you, and I appreciate you being here today. Thanks, April.
Thanks.
All right. Have a good day, everybody.